Hello again, everyone. So I just want to take a little time and go over the uh, Math in the Mole review work at the end of the packet. So it's pages 11 through 14. So let's take some time and go through these problems. And maybe if you had any issues, this might clear that up. All right. So question number one, this is on page 11, the practice math problems. Let's go through these first. All right. So number one, we got determining percent composition of iron. So percent composition, remember our formula here. So it's part over the whole times 100. So it's right on your reference tables. All right. It's on table T. So first thing we got to do is figure out how much the whole thing weighs. So how much does Fe2O3 weigh? So we list our elements, Fe and O, count them up, right? We've got two Fe's, three O's, times them by our masses that we get right off the periodic table. So iron is 55.8. Remember, we round to the nearest tenth. Oxygen is 16. All right, and we tally those up, and we get 111.6 grams, right, and 48.0 grams. Add that all up, and we get 159.6 grams, right? That's how much the whole thing weighs. That's pretty bad. G. Let me fix that. All right. Grams, right? So that's the mass of the whole thing. Now, all we care about here is the iron as the part, right? So I want to know what percent iron makes up of the whole thing. So here's the amount of the iron, right? So it's part over whole times 100. So 111.6 grams over 159.6 grams times 100. And we get 69.9%. So your units are percent, and that's our answer. All right. That's percent composition, part over whole times 100. Formula is on table T. All right, number two. Now, this is what we were doing the other day. So now this worksheet kind of goes through all the different math things that we've been doing in this unit. So if you're able to get through this all on your own, just using your reference tables and your calculator, then that's pretty good. That shows that you know what to do, when to do it by looking at the question and figuring things out, which is pretty good. All right, so let's look at number two. So remember, all these answers also are posted on the assignment in Google Classroom, so they're all attached, so you can look at that too without watching the video. So number two, a compound has an empirical formula of CH2 and a molecular mass of 56 AMU. What is the molecular formula? So this is when we have to figure out how much the building block weighs and then how many blocks it takes to make the whole thing, right? That's determining the molecular from the empirical, all right? So CH2, right, that's 12 plus 2, that's 14 grams, right? So CH2 weighs 14 grams. That's our empirical formula's mass. And then 14 goes into 56. We do 56 divided by 14 and we get 4. And that then is our multiplier, right? So now we multiply CH2 by 4 and we get C4H8. And that is our molecular formula, all right? So just think about the concept here. The empirical is the simplest whole number ratio of the molecular. So the molecular is always going to be a multiple of the empirical. So the mass of the molecular formula, that kind of tells us how many of the empirical formula units it takes to make up the whole thing. We just got to figure it out, right? So how many blocks does it take to make the whole structure? Done, right? Number 3 is now 2 parts, right? So sometimes they break these up. So first you got to do the gram formula mass, and then you got to do a mole gram conversion. That's a pretty standard type of question. So first thing we got to do is see how much the whole thing weighs. Na, N, and O. All right. So we've got 1 Na, 1 N, and 3 O's. We're going to times them by their masses, rounding off to the nearest tenth off the periodic table. So sodium's 23, nitrogen is 14, oxygen is 16, right? Tally all these up. So make sure you show all your work and you're nice and organized and methodical. So if you make a mistake, you can get as much credit as possible. If you just put an answer and it's wrong, then you get 0. So show as much work as possible. You're only hurting yourself if you do not. Grams per mole, right? So that is our gram formula mass. How much 1 mole weighs, right? 1 mole of sodium nitrate weighs 85 grams, okay? Now, once we know how much 1 mole weighs, we could figure anything else out from here. So now we have our how many moles of NaNO3 are in a 3.5 mole sample. So remember, moles equals grams over the gram formula mass, right? We always know the gram formula mass, so we're either solving for the moles or we're solving for the grams. In this case, we're solving for the grams, all right? So 3.5 moles equals X over 85 grams per mole. Set this over 1, cross multiply, and we get X equals 297.5 grams, right? Because moles over moles cancels out, and we're left with grams, right? And then the last one here is just one of the straight up stoichiometry problems. Weird name, but easy concept, right? So how do we do these? Well, we just focus in on the 2 substances that the question is referring to. So we've got H2SO4, I like to underline them, and aluminum. There's aluminum. So I don't care about anybody else. So here's your original equation. 2 moles of aluminum and 3 moles of H2SO4 makes 3 moles of hydrogen and 1 mole of aluminum sulfate. Remember, nothing means 1. So how many moles of H2SO4, that's our unknown, so that, remember, is our X, are needed to react with 5 moles of aluminum? So we set up the proportion right in the equation, pull it out, and cross multiply. Right? So we get 2x equals 15, divide by 2, divide by 2, and we get x equals 7.5 moles of what? H2SO4. Done. Okay? So if you could get through this whole worksheet without looking at your notes, just using your reference tables and your calculator, then that's pretty good. You can figure out what to do when, and these are most of the math things that we did in this topic. All right. So now let's move on to pages 12 to 14, which is some more review questions. The stuff I crossed out, obviously, you don't want to do those. So some of these are just pretty basic questions, but there's a couple that I want to go over. So I'm not going to go over everything, but I'll go over some of these. All right. Number 2, this is just like your straight up mole gram conversion. So in this case, they're giving you the grams. You got to figure out the moles. So you figure out how much 1 mole weighs, and then you do moles equals grams over gram formula mass, and you get 1.5 moles, right? So all the answers here to these are posted in the assignment. So you don't have to wait for me to give them out here. They're all there. You can check your answers. And if you don't want to watch this video, don't watch the video. All right. Number 3, which sample contains a total of 6 times 10 to the 23rd atoms? So remember what this number is. 6 times 10 to the 23rd atoms is 1 mole, right? So this is basically asking us which one is the molar mass, right? Molar mass. How much 1 mole weighs, right? How much 1 mole weighs. The molar mass. That was bad. Let's spread that out. It's hard to write. Hard to write in Cami here with the stylus I have. I'm doing my best. Molar mass, right? How much 1 mole weighs. We have all of this on the periodic table, right? We know all of our molar masses. Let's go to the periodic table right here. All right. We know the molar masses of every element on the periodic table. It's the atomic mass just in grams, right? So in question number 3, when it says which sample contains 6 times 10 to the 23rd atoms, that's 1 mole, or 6.02, right? We can have it either way. It could either go to the 10th, go to the 100th. So it's 1 mole. So it's all really just saying which one is showing its correct molar mass. So the answer is A, 23, because sodium's mass is 22.98977, which rounds off to 23, right? If we look at B, carbon, it says 24 grams of carbon. Well, if 1 mole weighs 12 grams, then 24 would be 2 grams. So that's not the mass of 1 mole. All right, choice C, krypton. 1 mole of krypton weighs 84 grams, right? So, my laser. No, it doesn't work here. So 84 grams is 1 mole. So if we have choice C, 42 grams, that's half a mole. All right. And then potassium, K, 1 mole weighs 39 grams. So if we have 78 grams, choice D, that's 2 moles. All right. So the only one that's associated with its correct molar mass is choice A, which is 23 grams of sodium. All right. So just understand what the molar mass is, and we have all that information on your periodic table. All right. So let's go back to the other sheet. How to get down here. All right. Next up, number 6. This is your percent error, right? That's on your reference tables. So remember, it's the measured minus the accepted, or just the difference, right? Because we were talking about using the absolute value bars. We don't care if it's negative or positive. It's the difference, right? So it's the difference over the accepted. So the important part is you put it over the accepted. So a student found the boiling point of a liquid to be 80.4 centigrade. Oh, that's why, because I went to the wrong thing. There we go. So this, right, is the measured. Measured. If the liquid's actual boiling point is 80.6, right? So that's the actual or the accepted, right? What's your percent error? So it's measured minus accepted over accepted times 100. So the key part is the bottom part has to be the accepted value. If you screw that up, automatically no good. So difference over accepted times 100. So that's our appropriate setup. And then if we did the math, we'll get the right percent composition. All right. Number 9. Which pair of formulas correctly represents a molecular formula and its corresponding empirical? So remember, the empirical is the simplest whole number ratio. So you're just looking which formula can be reduced to the other formula, right? So choice A, 2 to 2, right? 2 to 2 does reduce to 1 to 1, right? 2 and 2 are divisible by 2. So that's our answer, right? So let's look at the other choices. B, 3 to 4 does not reduce to 1 to 2, so that's not the correct empirical formula. 4 to 6 does not reduce to 1 to 1. And then 5 to 8 isn't even reducible. And then 2 to 2 doesn't reduce to 5 to 8. So that's the only one that's paired with its appropriate empirical formula. Number 10, a compound has an empirical formula of CH2 and a molecular mass of 56. What is the molecular formula? So that's the same thing we were doing before, right? You say, okay, how much does the building block weigh? And then how many times does it go into the mass of the whole thing? And then that's what we multiply our empirical formula by. And then we can figure out the molecular formula. So this again, carbon and 2 hydrogens weighs 14. 14 goes into 56. How many times? 4 times, right? 56 divided by 14 is 4. So then that gives us C4H8, right? Pretty simple. What else? Number 12, that's another percent composition, part over whole times 100. So in this case, I only care about calcium. So that's my part over the mass of the whole thing times 100. That's not too bad. I don't think I have to go into that any further. Number 14, only thing to watch out for here is remember what the parentheses mean, right? That 2 applies to everything inside. So we've got 2 nitrogens and 8 hydrogens, right? So when we're tallying up the mass of the whole thing, we want to make sure we get the correct amount. So we get the correct mass, which is 132 grams, right? But if you screw that up, then guess what? One of these choices is going to be the right answer when you make a mistake and mess it up. All right. So watch out. They know the mistakes that you're going to make. And one of those choices might look really nice if you made that mistake. So be careful and watch out. All right. Moving on. All right, number 16. This is what we were doing the other day when we were given the percent compositions and you want to determine the empirical formula. All right, so we got 14.6% carbon, 85.4% chlorine. What is the empirical formula? All right, so I'm going to switch to a blank sheet to do that one. All right, so this is number 16. All right. All it's telling us is that we have 14.6% carbon and 85.4% chlorine. All right. So remember how to do this. You just got to be methodical here. So put our elements, carbon, chlorine. All right. So first thing we do is take these percents and we turn them into grams, right? We assume we have a 100-gram sample. So if we have 100 grams, then our numbers are going to be the same. All we're doing is taking that percent and making it a G. All right, so that's step 1. Now we divide these by our molar masses that we get right off the periodic table. So carbon is 12 grams per mole. Chlorine, we round that off to 35.5 grams per mole. All right, now remember, any calculations you do from here forward, don't round anything off until the end. Take like 4 or 5 decimals off the calculator if you have to, but don't round until the end. Okay, so 14.6 divided by 12 gives us 1.21667. So I'm going to take that whole thing, 1.21667 moles. And then 85.4 divided by 35.5, I get 2.40563. 2.40563 moles. All right. So now this is our ratio, but it's not really a very simple ratio. So we want to try and simplify that. So the best way to do that is to divide all of your molar amounts by the smallest one, which is 1.21667. 1.21667. Right? Why do we do that? Because one of them comes out to be 1, nice and easy. And the other one should come out to a number that's pretty close to a whole number. So we get 1.997 ... So now we round. So that's 1, and this rounds off to 2. Right? The only time we don't round to a whole number is if it's close to a half. Then we go to the half and then multiply everything by 2 to get rid of that half and bring us to the nearest whole number ratio. So this is a 1-to-2 ratio. So that means our formula is CCl2. All right? As hard as that gets. Okay, so that's number 16. Number 17, we haven't really talked much about hydrates. There's a lab that goes along with this, but we haven't had a chance to do that lab. So a student heated a 9.1 gram sample. So we have 9.1 grams, all right? So he heated it of a hydrated salt to contain a mass of 5.41 grams. So a student heated a 9.1 gram sample of a hydrated salt to a constant mass of 5.41 grams. So he heated that and the mass dropped. Why did the mass drop? Because a hydrate, hydro water, has water molecules associated with the crystalline structure. We've talked about hydrates a while ago, right? So when you heat up a hydrate, you can essentially evaporate off all of the water, and then you're going to be left with a lighter mass sample in the end. So if you take the difference, 9.1 minus 5.41, we get 3.69 grams. 3.69 grams. That difference is the amount of water that was in your sample, all right? So if I want to know the percent of water that was in the sample, remember percent composition, part over whole times 100. All right, so if I want to know how much water, that's my part, 3.69 grams of water. The whole hydrate originally weighed 9.1 grams. And then don't forget you times 100. And we get 40.5%. Don't forget your units, percent, right? That's number 17. All right, what else? Number 19. Let's go back to the worksheet. Number 19. Which two compounds have the same empirical formula? So which of these both can be reduced to the same simplest whole number ratio? That's what it's asking you. So 2 to 2 reduces to 1 to 1. 2 to 4 is 1 to 2. So that's no good. 1 to 2, 3 to 8, not 1 to 2. Right? 1 to 1, 2 to 1, no. 1 to 2, and then 2 to 4 reduces to 1 to 2. So that's your answer. Right? That's just understanding the relationship between the empirical and the molecular formula. All right? Next one, number 22. 22 is a little tricky because it's easier than it looks. What is the ratio of moles of CO2 to moles of C2H6? All right? So we want to know the ratio of moles of CO2 to moles of C2H6. So the tricky part here is just which number comes first. So this wants to know the relationship between CO2 and C2H6. So here's CO2 and here's C2H6, all right? So there's 4 moles of CO2 to 2 moles of C2H6. And now 4 to 2 reduces to 2 to 1. So that's our ratio. For every 2 moles of CO2 in the equation, there's 1 mole of C2H6. So it's a 2 to 1 ratio. So the tricky part is they just kind of flip-flop the reactant and the product. So you got to think about which two things are you comparing and in what order. All right. But other than that, it's a pretty simple question. All right. So that's number 22. And then the last one I want to do is number 26. So this is another standard stoichiometry question. So which is the total number of moles of NH3? So remember, focus in on the two things the question's asking about. So NH3 and H2. So we don't care about nitrogen here, all right? So how many moles of NH3, that's my X, are produced when 10 moles of hydrogen react completely, all right? So if I have 10 moles of hydrogen, how many moles of NH3 am I going to produce? So we're assuming we have plenty of nitrogen. So if I have 10 moles of hydrogen, how many moles of NH3 can I produce, right? That's like saying if I have a ton of bologna and I have a certain amount of slices of bread, how many sandwiches can I make, right? Once I run out of bread, I can't make any more sandwiches, no matter how much bologna I have. But here's how many slices of bread I have. How many sandwiches can I make? All right. So we pull the proportion out. 10 over 3 equals x over 2. We cross multiply. We get 3x equals 20. We divide by 3. And we get x equals 6.66 repeating, which rounds off to 6.7 moles of NH3. All right. And that's as hard as stoichiometry will get, which is choice A. All right. So that's everything. That's the whole unit. So don't forget there's a unit outline at the end of your packet that goes over, just lists out all the top concepts that we covered in this unit. That's everything, right? If you have any questions about anything, feel free to send me a message. But that's the whole unit. So now you're ready for the test. All right. Good luck on the test. And I'll see you all on Friday for hot chocolate. Bye-bye.